Welcome back. We've been looking at smoothing methods. Today we're going to have a little bit of fun playing around with smoothing methods and computing the uncertainty in the smooth that we compute by various methods. Now you may recall we did that when we were looking at fitting functions with regression. Now we're going to do it with smoothing, and it's actually very similar the way that it's done. It's important. Smoothing is great for exploring data. It really is. It helps us identify possible signal by reducing the noise. But it is so much better when we have an idea of how uncertain our smoothed estimate is. Let's consider the simplest case, just averaging some data. We might split time into slices and average the data within each slice. The average, which I might call x bar, is just the arithmetic average of the data inside that particular slice. And that happens to be equal to the sum of a certain number of weights times the data values, but only within the window we're looking at. The W sub j are the weights, and for a simple average of n data points, all the weights are equal, and they're equal to 1 divided by n. Now suppose the data actually equals some mean value mu plus random noise values epsilon, so that x equals mu plus epsilon. Then the average is given by this, which we can apply the distributive law and get this. Now, consider the sum of the weights. We want to insist that the weights have to add up to 1. If there are n weights and they're equal to 1 over n, then their sum actually is equal to 1. So this sum becomes 1. So the smoothed value, the average, is just the true average, the mean value, plus the sum of weights times the noise. One consequence is that when the noise is zero mean, which we almost always assume to be the case, the expected values of the noise are 0, so the expected value of the average is the mean plus the sum of weights times expected value of noise, which is 0, so it's just the actual mean. Since the expected value of our average is equal to the true mean, that means that our average is unbiased, a very useful property. What about its uncertainty? We can express the squared deviation by this formula. It's the sum of weights times noise values, at least their expected values, squared. And that's the sum over two indexes of weights times noise values. Well, the variance is the expected value of that squared deviation. And that's the sum of weights over two index values times the expected value of the product of two noise values. And that's the sum of these weights times the variance-covariance matrix of the noise. Because remember, the expected value of the product of two noise values is the variance-covariance matrix of the noise. When we have white noise, which is almost always the assumption applied by programs that compute things, well, the variance-covariance matrix is some constant, sigma squared, the fundamental underlying variance, times the Kronecker delta, which is 1 when the index values are the same and 0 otherwise. That means that the expected value of the squared deviation is this term. This particular term, the Kronecker delta, is 0 when j is not equal to k, so all those terms drop out of the sum, and we're left with this. When all the weights are equal to 1 over n, which they are for a simple average, that becomes sigma squared times the sum of 1 over n squared. There are n terms. Each one is 1 over n squared, so they add up to 1 over n, and our total variance of our average is given by this. This is an extremely well-known formula for the variance of an average. Nothing new, nothing remarkably groundbreaking or earth-shattering. It's the same old standard formula for the variance of an average, but here we've derived it by considering how it actually behaves when we compute the average. Now, the uncertainty is probably better described by the standard deviation than the variance. Just remember that the standard deviation is the square root of the variance, so the standard deviation of our average is sigma standard deviation of the noise divided by the square root of the number of data points going into it. Then we can define an approximate 95% confidence interval. as extending from average minus 2 standard deviations to average plus 2 standard deviations. By the way, when we speak of the standard deviation of the noise, we usually just say standard deviation. When we speak of the standard deviation of the average, or of a smoothed value, or of a parameter in a model, we usually call it the standard error, sometimes abbreviated SE. Now suppose there's an underlying trend. So the data aren't constant plus noise, instead there's some straight line plus noise. We could express the straight line as beta naught plus beta 1 times the time minus the midpoint time. T mid is the midpoint time of the interval over which we're averaging. The value at the midpoint time of the data we're averaging, that's what we really want to get. We want to estimate the smoothed value at that middle point of the time window we're looking at. Well, we can plug in the algebra again. We can say that our average is the sum of weights times that. That becomes the intercept term of our straight line times the sum of weights. That's what we're really looking for. Plus the slope within our window we're averaging over times the sum of weights times the difference between time and midpoint time, plus the sum of weights times noise. Well, we still have that the sum of the weights is equal to 1. We kind of insist on that for our weight function. Also, when the weights are centered at the midpoint of time of the window we're averaging over, and the times are evenly spaced around that midpoint, it necessarily follows that the sum of the weights times the time differences are equal to 0. That's because for each weight to the right of the midpoint time, there's an equal weight to the left of the midpoint time. And when we compute this sum, we get a positive offset on the right-hand side and a negative offset on the left-hand side. They cancel each other out. So this particular sum turns out to be 0. And that greatly simplifies our previous formula. We'll end up having this, that the average we compute is equal to the true value we're looking for plus the sum of weights times noise values. Now this tells us that the estimate is still unbiased, even when there's a slope that is active and noticeable within the window we're averaging over. That is an extremely useful quality. Also, we can apply the same formula. Generally, when we sum weights times data values, the weights sum to 1. The times are evenly spaced, that's the usual case, and the weights are symmetrically distributed about the midpoint of the averaging interval. That's the case for the filters that we considered in the last lesson. So the weighted sum is an unbiased estimate of the value at the time midpoint. This includes averages and filters with symmetric filter weights, like the tent filter, for instance. Now the general formula for the averages and for filters with filter weights W sub j, when dealing with white noise, we require that the sum of the weights is equal to 1. And to get an unbiased estimate, and the variance of the estimates is going to be equal to the variance of the smoothed value equal to the noise variance times the sum of the squares of the weights. By the way, generally we insist that the weights add up to 1. Sometimes we will specify a weight function where the weights do not add up to 1. This is easy to deal with. One way to do it is just to scale the weights so that they do add up to 1. Alternatively, you can just compute the estimate as the smoothed value or average or whatever you call it is the sum of weights times data values divided by the sum of the weights. And the sums happen only over the window that we're looking at to compute a smoothed value. We can compute its variance as the variance of the average, or a smoothed value, is the noise value times the sum of the squares of the weights divided by the square of the sum of the weights. I have made available some R programs to do some smoothing and some for some of the filters that we considered last time, and for the Gaussian smooth. There are 2 files you can download, timav.csv and gauss_smooth.csv. But when you do download them afterwards, rename them as timav.r and gauss_smooth.r. The reason I called them CSV for downloading is that WordPress won't allow me to post an R file or a text file, but it will allow me to put up a CSV file. So I put them up as CSVs. It's just a little game I'm playing. Go ahead and download them and rename them, and then they'll be ready to go. There are a bunch of functions included in these two files. One of them is the TimAv function, and you call it by saying that something is equal to TimAverage of t being the times, x being the data values, and a times scale over which to average. I called the something q because q is the variable name I use for just some generic quantity that I'm probably going to throw away later on. The other file actually loads three functions. One of them is called boxcar filter, and you call it by saying I want q, something, to be the boxcar filter of my data, and I want my boxcar filter to be n data points wide. Notice I didn't specify the time here. The boxcar filter kind of assumes that the times are evenly spaced, so you don't really have to tell it what the times are in order to be able to compute the boxcar filter. Another function is the tent filter. It's called by saying compute the tent filter of the data x and make it n wide points wide. The final one is the Gaussian smooth. You call it as Gauss.smooth of t being the time, this time you need to specify that, x being the data values, and t scale being the time scale of smoothing. Notice there's a difference. For the boxcar filter and the tent filter, I don't even have to tell it what the times are. And I don't give it a time scale, I give it a number of data points scale, the number of data points width of the filter that I'm going to use. For a Gaussian smooth, I tell it what the times are, and I tell it what the time scale is. That's because the Gaussian smooth can be applied even when the times are not evenly spaced. So for uneven or irregular time sampling, you can use a Gaussian smooth, but then you need to specify the scale of smoothing as a time scale, not a number of data points scale. By the way, these functions also have an option called plot, and if you also add plot equals true or plot equals capital T for true, it'll produce a plot for you, so you can call them in the same way, but with this plot option, it'll just make a nice little plot for you.